All right, here is the test for review. I'm going to walk through most of the question here for you. Hopefully, it will help you understand better when you look at my answer key. Number one, we want to find a basic and the dimension for the orthogonal complement of the set S span 0, 2, 3, 1 and 4, 1, 0, 0. So let me remind you is that the dimension of R4 is equal 4, right? And the dimension of S is apparently 2, because there are two vector there. Right? So this implies the dimension of the orthogonal complement S is equal to 2. According to the definition of orthogonal complement, we want to find all vectors, plural, that the dot product with the vectors in the basics equal to 0. So that means we have two vectors there in S. So that means vector 0, 2, 3, 1 dot x1, x2, x3, x4 is in R4, right, is equal to 0, and the remaining F vector, which is 4, 1, 0, 0, dot x1, x2, x3, x4 is equal to 0 also. Right? Now, this can be written as A transpose dot, A transpose U equal vector 0. Right? That means, let's see, maybe I'll use black. I have 0, so transpose those two columns is going to become 2 rows. So 0, 2, 3, 1, and 4, 1, 0, 0. And then do we still have x1, x2, x3, x4? Notice that this is, the first one is the 2 by 4 and a 4 by 1. Okay, so the inner dimension is the same. You can multiply matrix C. And then the outcome should be what? 2 by 4, right? I'm sorry, 2 by 1 will be the outer dimension. So equal 2 by 1 is equal 0, 0 is 2 by 1. That makes sense. Let me rewrite my 0. It looks like 8. Okay. All right. I'm running out of space. I'm gonna go down here in the number 2. So you can do okay. So here I'm gonna transform it into system of equation. So I have, let's see, I have 2x2 plus 3x3 plus x4 equals 0. And then the second equation, I have 4x1 plus x2 equal to 0. Notice that x2 and x4 are free variables. So I'm going to let x2 equal s and x4 equal t. Right, so that's imply. So that's imply what? That's imply. Maybe I'll save space out right here. Imply x1 is negative s over 4, right? And x3 is t minus 2s over 3. All right, so the solution in order pairs, x1, x2, x3, x4 is equal to negative s over 4s, and then negative t over 3 minus 2 over 3s, comma t. I can factor out s, right, to extract the basic. So here if I extract s, I have negative 1/4 for the first component, and then 1, and then negative 2/3. There's no t there, so it's 0. There's no s there, right? And if I extract t, then I have 0, 0, negative 1/3, and 1. So we can conclude that therefore three dot mean therefore the orthogonal complement S is the subspace with basis equal, right, when I space equal negative 1/4, 1, negative 2/3, 0, and 0, 0, negative 1/3, 1. And we're done. Number 2 is about linear regression, approximation of linear regression. This problem is not hard, but it's just a lot of computation. I'm going to do a setup for you, and you can do the computation yourself. Okay. It's not hard. It's just a lot of computation. Okay, so let's see. We're given a table, and we are told to find the least square regression cubic polynomial. Just highlight it here. Maybe I'm doing blue. For the data, then used to predict the revenue in 2015. Let t represent the year with t equal to 3. Okay, so 2003 is x is going to be 3, and then y is going to be 1.5. Right, so I have a bunch of, so let me I have a bunch of point here, right? So I got what? I got 3, say I got 3 comma 1.5. I got 4 comma 3.2, 5 comma 6.1, etc. Right. So I can and on and on. I don't want to write them all down. So the quadratic regression is, oh, not quadratic, is cubic. Is a cubic regression. Regression equation is y equal c naught plus c1x plus c2x squared plus c3x to the x cubed. So in this problem, I'm going to write out a first few equations. So the first one, say I have 1.5, that's my y, right? C naught is my constant, plus C1 is 3, right? 3x, what should we say x? 3x1, oh, sorry, 3x, plus sorry, 3c, this x is 3, 3c1 plus x squared, 3 squared is 9, so 9c2. I really tempted to say x again. Plus 27, don't I keep saying that, c3. 3 cubed is 27. And then the second one would be what? 3.2 equals c naught plus 4c1 plus 16c2 plus 64c3, right? And then all the way to what? All the way to 2010. So the y is 29.3 equals c naught plus 10c1 plus 100c2 plus 1000 C3, and then you plug that in your calculator. We're gonna use, well, it's gonna give you a no solution, right? So we're gonna use the normal matrix, which is A transpose A x equal, I forget, let me look it up, forgot this part. A transpose B. Right. So what you're gonna do next is, I'm not gonna write out because I'm first of all, I've run out of space. A transpose, first you're gonna plug in your calculator, input your matrix A, and then compute A transpose A. And then something in there, and then you compute A transpose B. And then you do REF, you set them together, you do REF. You should have C naught, the value C naught, C1, C2, and C3. And there you have your cubic equation, right? And then you can plug in the value they want to predict, right? That's the easiest part. 2015, so plug in 15 for x, that's all. Okay. All right, number 3, find a unit vector orthogonal to both u and v. Unit vectors, so it's going to be the vector divided by its length, right? So first we need to find the cross product of u and v. So u cross v will be I, j, k. And then here 2 vector, 2, 4, 2, 3, 5, 1. And now you find the determinant of minor a, j, k, right? You remember the minor. So so the component I, if I cover its row and its column, then the determinant would be 4, 2, 1, about 5, 1, right? Crisscross subtraction, so 4 times 1 is 4, minus 2 times 5, so 4 minus 10 is negative 6, I. What about j? 2 minus 6. And then don't forget the sign as well. Plus, minus, plus, right? 2 minus 6 is minus 4, which is another minus in front of it, which is plus 4. So plus 4j. Let's see, k. 10 minus 12, minus 2k. Now we're going to find the length of u cross v. Sometimes people call it norm. So the length is going to be just the coefficient of each component square, right? So we got 36, 6 squared 36, or negative 6 squared is 36, plus 4 squared 16, and 2 squared is 4. So this is root 56. You want to simplify that will be 2 root 14. Okay, now the final answer. We want to find the unit vector, so it's going to be the vector divided by its length. I didn't write the little arrow on top, but in this case, we both know that is I implying vectors, right? Not just a letter. So 1 over 2 square root of 14 times the vector -6, negative +4, -2. Dividing by the length is the same thing as times 1 over the length, right? So simplified, I have the unit vector is -3 over root 14, 2 over root 14, and -1 over root 14. Number 4, a parallelogram with U and V as the adjacent sides has the area of the length of U cross V. Find the area of parallelogram with the vertices following. So first I'm going to draw this to see what happened. It's going to be in the first quadrant because they all positive. Maybe to the left a little bit. Okay, so see, I'm gonna scale it out. See, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. Okay, so the first one, let me leave color code here. So I'm gonna call this A, point A, and then the second one I'm gonna call it point B. The third one I'm gonna call it point C, and then the last one is point D. Okay, so let's draw this A, 1, 2, right here. And that's my A. B is 4, 4, 1. It's just 4, 4, right? 4, 4. 1, 2, 3, 4. 1, 2, 3. I bought very well. 1, 2, 3, 4, 4. What's up here? Anyway, okay, and then 7, 5. 7, 5 must be up here, and then 4, 3. All right, let's connect the dot. See what happens. It's not the best one, but it's a parallelogram, right? Okay, so vector u is gonna be b minus a, right? ba, so b minus a. Keep with the color code thing. B is red, A is black. I'm doing this because when you read back my solution, it's easier to understand. And C minus B, and vector V vector v equal c minus b. All right, so let's find those. Vector u first equal b is 4, 4, 1 minus a is 1, 2, 1, which is equal to 4 minus 1 is 3, 2, 0. And vector v equal c, which is 7, 5, 1 minus vector v is 4, 4, 1 equal 3, 1, 0. And then the area is the length of u cross v, right? Maybe I'll run out of color, so I'm going to use purple here. So u cross v I, j, k. I got 3, 2, 0, and then 3, 1, 0 equal. All right, I, the component I, 0, right? 0. Component j, also 0. And then component k, well, minus 0, so still 0, is 3 minus something wrong here. BA, so B is vector, see vector U. Let me see vector U. B, C, D. And then CB, so it should be B minus C, right? C, B minus C. Okay, so this chain of, so negative 1 here, negative, negative. Something not right. Oh no, I don't know why. It's okay. Yeah, it's 3. That's right. I don't want to change anything. We was correct in the first time. Sorry. Okay. All right. We was correct in the first time. All right. And then the last component, K, is 3 minus 6, so negative 3K. All right. Okay. So U cross V, length of U cross V is 0 squared plus 0 squared plus 3 squared, which is root 9, which is equal to 3. You want to be careful. You can put square unit. All right. Number 5, the volume of, I'm not sure how to pronounce this, parallel the pipette. Anyway, Well, actually, it's already given to you right here. You have to do is just compute that, right? Do the cross product between v and w first. Then you get a vector and you dot it with u, and then you get a scalar. Right, so it's computation. I'll let you do it yourself. The formula is right there. Number 6, find the image of v and the preimage of w. So let's talk about some terminology. So I have two bubbles. Say I have two bubbles. The first bubble is let me make it red. It's fine. The first bubble is the domain. Right? We call this the domain. And the second bubble is the codomain of the range. Right? So in the domain, I have V, right, which is the preimage of T of V. Right? So vector V equal -3, 2, 5. And in the codomain bubble, I got the image TV, which is T equal -3, 2, 5. Right? Okay. So the image of V, which is T of V here, T of the vector V here, is T of what? -3 to 5. Then if I want to find T of U, so the image I color in blue. T of U is what? It's right there, right? Right here. Right here. All you have to do is just replacing your value for V1, V2, and V3. Right? Let me remind you that's V1, V2, and V3. Right? So let's see what happened. I got 3 V1 minus V2 plus V3. So 3 times -3 minus V2, which is 2, plus V3, which is 5. And then the next one, I got what? I got V1 plus V2, so -3 plus 2. And then the last one, V2 plus V3, so 2 plus 5. So I got -6, -1, and 7 for the image of V. For the preimage of W, just T of V1, V2, and V3, which is equal to what? Equal to the image, which is -3. I'm sorry. The preimage is 0 to 5. Since I bought the wrong number. 0 to 5. And again, you plug it in, right? The first one, I have what? 3V1 minus V2 plus V3 equals 0. The second, I have what? V1 plus V2 equal to 2. And then the last one is V2 plus V3 equal 5. We can use calculator to do this. I did it before, so let me tell you what the the answer is. So I got V1 equal -1/5. V2 is 11/5. And V3 is 14/5. Number 7, prove whether the function is a linear transformation. If it is, then phi is standard matrix. Now, how do I prove something is a linear transformation? If you want to prove something, your best bet is to go back to the definition. Right? So linear transformation satisfy addition and scalar multiplication. Right, so those are the two things we have to prove. The first one, A, C A. Let's prove addition first. So I want to prove that T of A plus B is equal to T of A plus T of B, right? Let's say A here, just let's pick 2 points. Let's pick 2 points to see, pick 2 points. You're gonna pick A equal to 1 and B is 0, -3. So this implies that A plus B equal 2 minus 2, right? So let's do the left-hand side first. T of A plus B is equal to what? Well, you go back to the problem they gave you here. I have x1 plus 3, comma x2. So x1, remember this is your x1 and this is your x2, right? So x1 is 2, 2 plus 3, comma x2, so -2, which is 5, -2. Now, T of A plus T of B, the right-hand side. T of A is, T of A again, you using the formula. Here's your x1 and here's your x2. x1, x2, right? So x1 is 2, 2 plus 3 is 5. x2 is 1 plus, now go to B, T of B, right? So plug in 0 for x1. 0 plus 3 is 3 and -3, which is equal to 8 and -2, right? So definitely they're not the same, right? So the two things are different. They're different, right? Imply what? This imply, I write too large. Imply T of A plus B is not equal to T of A plus T of B. So the addition is failed. Therefore, it's not linear transformation. All right, what about the second one? All right, addition first. So say I want to prove that T of x plus y is equal to T of x plus T of y, right? Or better yet, in this case, I want to prove t of little x1 plus little x2, comma y plus y2, y1 plus y2 is equal to t of x1, y1 plus t of x2, y2. I'm going to start out with the right-hand side first. I'm going to start out with this side first. So let's go here. So the right-hand side, RHS, is t of x1, comma y1 plus t of x2, comma y2. We're going to use this expression, right? We're going to use that. X plus y at comma y. So that means what? It's going to be, so remember, x plus y, comma y. Okay, all right. So it's gonna be x1 plus y1, comma y1, plus x2 plus y2, comma y2. Oops, let's see there. Okay, adding component to component. So I have x1 plus x2 plus y1 plus y2 for the first component. And the second component is y1 plus y2. Which is, I can write it like this. I can write it as x1 plus x2 plus y1 plus y2, comma, run out of space here. Maybe I'll go down here because I want to write it in one line. Y1 plus y2, which is equal to the left-hand side, right? Is equal to, let me put this like this, equal to the left-hand side, which is this equal to, let me equal to this, equal to that right there, that the above green expression is t of x1 plus x2, comma, y1 plus y2, right, which is equal to the left-hand side. Done. So it is satisfied the addition. Now for the scalar, I want to prove that t of c times xy equal t of cx, comma cy. So t of cx, comma c, let me start out with the right-hand side first. So, all right. Right-hand side, t of cx, cy equal to cx plus cy, comma cy, right? It's, again, you use that thing here. Okay, all right. I can factor out the c. So x plus y, comma y here, which is equal to c times, that's t, right? This part right here, that's t. So c times t of xy. which is equal to the left-hand side. By the way, I can move this guy out like that. It's fine. Okay, so it is satisfy the linear transformation. Now we're gonna find the standard matrix. Okay, do some recording. Standard matrix. Let's say let A be the standard matrix. Then I got A times xy is equal to what? The x, the component is x plus y and y. Wait, how do I solve for A? Well, multiply both sides by xy inverse, right? Make sure if you multiply something to the left, you do the same thing to the right. You multiply to the left as well. Because matrix multiplication is not commutative. So A is equal to, if you multiply AXY inverse to the left, then it's just the identity matrix, right? A times I is still A. So A XY inverse, and then X plus Y, Y. And that's it. That'll be your standard matrix. Let's see, number 8. Yeah. All right. So notice that the basics are not the standard matrix is the standard is not in basics form. So we're gonna write like this. The image is t of 0 to -1. So 0, the image is I'm sorry, phi t of 0, -1. 0, -1 is equal to C1 1 1 plus C2 2 -1. Yep. So now we can transform this into a system of equation. I have 1C1 plus 2C2 equals 0. And I have 1C1 minus C2 equal -1. You can use REF. We're going to use elimination here. Multiply the second one by 2 so that I have C1 plus 2C2 equals 0. Same for the first equation. The second equation, however, is double, right? 2C1 minus 2C2 equal -2. And then you add, this is gone, that is gone. So I got 3C1 equal -2. That means C1 equal -2/3. If you plug it in the second equation here, I want to solve for C2. C1 is negative, you can write it in blue, -2/3 minus C2 equal -1. I want to solve for C2, so C2 equal 3 minus 2/3, 1/3. Okay, we're not done. we find the image of t, right? So t of 0, -1 equal, let's see, C1 is -2/3 t of 1, 1 plus 1/3 t of 2, -1. T11 is 2/3, 2, 3, right? 2 and 3 plus 1/3. T2 -1 is 1, 0. So I have the first component is -4/3 plus 1/3, which is -3/3, which is -1. And then the second component is I have -2. -2 plus 0 is -2. And then we're done. All right. Number 9. Find the basics for the kernel and the range of t. Then find its nullity and rank. Nullities mean the dimension of a kernel t, right? So let me remind you here. Nullity is just another name for the dimension of kernel t. Okay, all right. First find the basic of the kernel. So according to the definition, the kernel of t is the set xyz. In this case, I'm just kind of doing definition that in term of this case. So of course in R3, right? And we have 2x plus y plus 3z, x plus y, and then y minus 3z is equal to 0, 0, 0, kernel, right? We can write it like this. It's gonna be 2x plus y plus 3z equals 0, and then x plus y equals 0, and then y minus 3z equal 0. If you do RREF, what do we get? We get 1, 0, 3, or 0, 0 here. 0, 1, -3, and then 0, 0, 0 here. Right. If I let z equal t, so let me rewrite this. I'm gonna rewrite this before I let z equal anything. Transfer back. I got x plus 3z equals 0, and then I have y minus 3z equals 0, and then I have 0 equals 0, right? So now I know that I have infinitely many solutions. So here, if I let z equal t, then that's imply y equal 3t, and x equal -3t. Okay, so the kernel, so therefore the kernel of t is -3t, 3t, and t, where t is just a real number. Then the basics of kernel of t is -3, 3, 1. Here you can say that the dimension or the nullity of kernel T is equal to 1. Also, notice that this is linear independent, so of course it is span. All right, now we find the basics of the range T. We kind of did it there in red. If you notice that, by the way, we're looking for the rank. In order to looking for the rank, we need the rank is just the rank of T is the same thing as saying the dimension of range T. Right? In order to find range T, we need to find the basis of range T, dimension of range. So if you look at the red matrix right there, I kind of do the REF. So you notice that we have two basic column here, right? So that's imply what? That's imply the basics for range T is equal to what? Equal to 2, 1, 3. Oh no, I'm sorry. It's a column. It's a column. So yeah, 2, 1, 0, 2, 3. Yeah, 2, 1, 3. Sorry, 2, 1, 3. And 1, 1, 0. Right, so as you can see, the dimension is the dimension. Yeah, use this color maybe. If you look at here, dim of range T, which is equal to rank T. Oh, we don't have space. I'll go down here. To the left slightly bit, which is equal to rank T, rank T, which is equal to 2, right? Yep. Box though 2, that's the answer. And you can box the group blue too, but I don't have enough space. Number 10 is T invertible. Why? Let's see. We have T is R2 go to R2. All right, matrix A. Let's see. We have negative Y and X. Right. So for the first component, there's no X, so 0 for X, and negative Y, so -1 for Y. Right. And the second component, there's X, so 1X, but no Y, so 0. If you do the determinant of A, then it is equal to 1, which is not is not 0. So that means what? That means this implies A inverse exists. Therefore, T is invertible. Now, if T is invertible, then this implies it is equivalent to saying that T is 1-to-1 and it is also onto. If you take discrete math, they call it surjective and injective, I think. And together they call it bijective. Anyway, so the point here is that T, if it invertible, then according to theorem, I believe it's 6.12, T is also isomorphism or isomorphic, isomorphic, and this because of theorem that I think you can double check that. And by the way, the definition of isomorphism is is 1-to-1 and it's also onto. Okay. Okay, number 11, determine whether the linear transformation T from R3 to R2 represented by the matrix A is 1-to-1, onto, or neither. Then explain why. All right, so let's check 1-to-1 first. Let's check 1-to-1. Right, I denote 1-to-1 is red here, onto will be blue. So if it 1-to-1, then if the kernel of T is equal to 0, I meant 0 vector, right? Let's check the determinant of A. Well, definitely undefined, right? Because of the dimension. It's not even a square matrix. It's undefined. This imply what? This imply there is no unique solution, right? Thus, kernel of T, let me rewrite kernel of T properly. Kernel of T is not equal to 0. This implies T is not what? T is not 1-to-1. In order to prove that it's 1-to-1, you need to prove that the kernel of T is equal to 0, but in this case not, so it is not 1-to-1. Now, the second one, is it onto? If it's not 1-to-1, then is it 1-to or onto? Well, we don't know, we have to show. How do I show something is onto in this case? It's onto if, well, we want to show, move it down here a little bit. We want to show that the dimension of range of T is equal to the dimension of the arrival. By the way, the dimension of ring T is called ring T. Okay. Let me remind you the dimension of arrival. If I go back up to the question here, I have R3 to R2. R3 is end. R3 is n. Right there. R3 is the dimension of the domain. That's the dim of the domain. right? which is n, which is the n is 3 here, right? And then R2 is the dimension of the arrival. Okay, now we need to show that if it on 2, then the dimension of the arrival had to be equal to the dimension of the ring T, which is equal to 2. Right? See if the dimension of ring T is equal to 2. We're gonna start with n equal, we'll start with this equation, n equal, move down a little bit, n equal dim of the kernel of T plus dim of the range of T. And let me remind you, the range of T is we call rank, sometimes we call it rank T, right? Rank T. All right, n is what? N is 3. Well, what is the dimension of a kernel of T? Well, you have to solve for it, right? You can do REF for this one. I'm gonna do REF for A. Maybe let me go down here. Then I say REF. If you do the REF, use your calculator to do that. Everybody should know how to do that very well by now. I got what? I got 1, 0, 0, and then I have 0, 1, 1, 0. Right? So if I change it into system of equation, I got x equals 0, and then x plus y equals 0. If I let z equal s, then y equal negative s. Right? So x, y, z is 0, negative s, s. Better yet, if I factor out the s, I got 0, negative 1, 1. So 0, negative 1, 1, that's the basics, right? So the dimension of a kernel T, which is the number of basic, which is equal to 1, right? So dim of kernel of T is equal to 1. Right? So here is 1, just put 1 there. Plus dim of range T. So now you can solve for the dimension of range T, which is what 3 minus 1 is, which is 2, which is equal to the dimension of the arrival. So yes, you can conclude that T is on 2. All right, number 12, find the matrix relative to B and B prime of the linear transformation T. Then find the transformation B prime. Right? Okay, so let me remind you of something. If I want to find M B from B to B prime, then here I have T of V1, right? And some value here, and T of V2, some value here. And I'm going to express this in term of B prime, right? This here is 2 by 2, of course. Right, so T of V1, what T of V1? Oops. In this case, gonna be 2 T of 2, 1, right? T of 2, 1, which is equal to what? T of 2, 1, T of 2, 1. We're gonna express in terms of B prime, so so it's gonna be, let's do the B prime first. Let's do the B prime first. So equal to C1 negative 1, 0 plus C2 to 2. And then we're gonna use this. Oh, okay. TXY, right? 2y comma 0. So 2y comma 0, 2y is 1. Remember, this is your x, this is your y is 1. So 2, and then, well, the second component is 0, so it's always 0, right? And then TV2 is T of negative 1, 0. Let's see, use the same thing, 2y comma 0, right? So x is negative, remember this is your x, this is your y, x is negative 1, y is 0, so y is 0, so 2 times 0 is 0. And then second component is always 0. C1, C1 negative 1, 0 plus C2 to 2. All right. So from the first one, I can solve for C1 and C2. Yeah. C1 is negative 2, and then C2 is 0. Same thing with the second one. C1 is 0, C2 is 0. So now T of V prime is equal to, let's see, I got negative 2, 0, and then 0, 0 here. I need another matrix. So I got 2 by 2, remember 2 by 2, and then I need a 2 by 1 here, right? And then my result is going to be a 2 by 1. So how do I get that? I need the purple one. So now negative 1, 3 equal to C1. You do the same thing like you did before. 2, 1 plus C2 negative 1, 0. And here you can solve C1 equal 1 half and C2 is negative 3. So fill it in 1 half and negative 3. And then you multiply together, you should get the answer. Okay. Number 13. Number 13. Find the matrix A prime for T relative to the basics B prime. I think this is considered is relatively easy problem, right? Because we have the standard basic vector. So this one right here, This one, oh, too dark. This is the matrix A standard to SD to HD. Right. Okay, so P is B prime, which is equal to 1. Let me do the columns just easier. 1, 1, 0, and then 1, negative 1, 0, and then 0, 0, 1. Then P inverse is equal to you can pause and compute the P inverse. I'm going to do the same. I got 1/2, 1/2, 0, 1/2, negative 1/2, 0, 0, 0, 1. Right. Now, A prime is equal to A B prime to B prime, right? Which is equal to what? P inverse times A standard to standard times A times P here, right? All right, just plug it in. What's P inverse? P inverse is this one. I'm gonna duplicate it, this one. And A, your A is gonna be 1, 1, 3, 0, 3, 1, 0, 0, 0, negative 2. And then P, this one. Okay. Plug in your calculator. I'm gonna pause it here. I got 4, 0, 0, 0, negative 2, 0, 0, 0, negative 2. And then we're done. Number 14, Daniel did this in section 6.4, number 12. So you can take a look at it. I'm not going to do this because the answer is there. It's not there, but similar, right? Similar to number 12, section 6.4. We did this in lecture, so I'm not going to do this again. It's pretty straightforward. Okay, number 15, use the matrix P to show that the matrices A and A prime are similar. So we want to show that A and A prime are similar. This means A prime equal P inverse AP. Okay, so well, we know A prime is 5, negative 3, negative 4, 1. Now is it equal to P inverse, which is 3, negative 5, 1, negative 4. And of course, take the inverse. A is 18, negative 19, 11, negative 12. And P is 3, negative 5, 1, negative 4. Plug this in your calculator. Then it turned out to be equal to 5, negative 3, -4, 1. I did it beforehand. So it is, right? We're done. Number 16, the last one. Determine the matrix that produce a 120 rotation about y-axis. So let's see, we have 120 degree about y. And then we have a 45 degree about the z direction. So this is my ry, and this is my rz, right? And we know the formula r equal rz times ry. Okay, rz is going to be what? Going to be cosine of 45 degree, negative sine of 45 degree, and 0 here. And then we have sine of 45 degree, cosine of 45 degree, 0, 0, 0, 1. Be careful about the sine. Right? Y is cosine theta, then 0, sine theta, and we have 0, 1, 0. Then we have sine theta, oh, no, negative sine theta. See, be careful with the sine. 0. Then we have cosine theta. Okay, so cosine of 45 is √2/2. Negative sine 45 is negative √2/2. 0. Oops. Then we have sine 45, √2/2, √2/2, 0, 0, 0, 1. Oh, I forgot to plug in the 120. I should have just put it in here. 120, 120. Right, cosine of 120 degree is negative 1/2. And 0 sine of 120 is √3/2. 0, 1, 0. And then we have negative √3/2 here. 0. And we have negative 1/2 again. And then you plug in your calculator. Wait, I didn't do this part. Then you're done. Just be careful with the sign. Maybe I'll put it here. Careful with the sign. All right. Again, I'll be out of town for the whole week next week from the 13th to the 20th. So I'll be literally out of state. So it's probably gonna be hard to reach to me. I'm not sure the internet is even stable. I hope the video will help. If anything, please reach out to Dan. Go to his office hours. Right. All right. Good luck and see you again next time.